Welcome. I am Pete Kostick, the president of Robust Analytics, and I appreciate this opportunity to talk to you today about some of our recent research. Robust Analytics is a small R&D company that focuses on building aviation safety and airline operations decision support tools to help airlines and the FAA to improve the safety and efficiency of flight operations. Much of this work was sponsored by the NASA System-Wide Safety Project, with the outcome a suite of applications to monitor and predict safety margins in terminal airspace. The research continues, and I hope to receive feedback from you and possibly collaborate on current and future projects. I will open by describing our approach and motivation for this research, beginning with methods we developed to predict terminal area safety margins, followed by a description of our more recent work that aims to perform continuous real-time monitoring of terminal airspace hazards and risk events. There is, of course, a large literature on aviation safety, and it concludes pretty conclusively that crashes and other unsafe events have precursors or risk factors that can lead to those events. These risk factors include weather, infrastructure outages, traffic density, fatigue, and workload. We got started on this work several years ago when we observed that many of these risk factors are predictable several hours in advance. And if that is the case, then we should be able to design and build a system that predicts when combinations of conditions will degrade safety buffers. The FAA uses the phrase going red when high altitude en route sectors are predicted to be unable to safely handle the traffic headed toward it. We wanted to design a similar system for terminal airspace. The system would be designed to be used by an FAA TRACON shift manager or an airline dispatch manager. Each wants to know what possible safety challenges they may face over the next several hours. So why is there no such system available today? The terminal airspace is more complex and dynamic than en route. There are many more risks and hazards. The traffic density is higher and operations are less predictable. There are many sources of data on potential hazards and flight risk, but they typically come from different sources at different times and without any assessment of interactions, dependencies, and how combinations of conditions can increase risk. Safety-related events commonly are caused by a combination of hazards, but airlines currently lack systems to identify those combinations of conditions that increase risk. Reliable forecasts of evolving safety conditions do not exist, forcing operators into reactive modes that prevent effective planning and mitigation. The technical challenge in designing such a system is that we need to identify multiple hazards, understand how combinations of conditions affect risk, and then predict when unsafe combinations of conditions may occur. I mentioned that we were interested in forecasting when conditions may degrade safety, but we also want to measure the changing frequency of safety-related events. Continuous measurement complements the forecast by detecting trends. I will cover both the prediction and monitoring systems in this talk. So there are many possible hazards in terminal airspace. Which hazard should we monitor first? Fortunately for us, we were able to use NASA research from a few years ago from their study analyzing terminal area hazards. They classified the hazards into three categories: airspace, environment, and human workload. We started our research by selecting hazards from each of these categories. Over time, we continue to add to the set of hazards that we monitor. We have lots of weather factors, some airspace hazards, and a couple of proxies for workload and fatigue. Most of our research is focused on examining terminal airspace and predicting safety margins using forecasts of risk factors multiple hours ahead. Based on some historical analysis of these risk factor values and combinations, we classify the airspace safety margin state as green, yellow, or orange. If we are connected to an airline's internal systems, we also have the ability to add proxies for possible crew fatigue and any equipment issues with the aircraft. One other important issue is that not all terminal hazards can be forecasted hours in advance. Examples of these hazards are turbulence, late flight plan changes, and high crosswinds. We add these potential hazard exposures to the monitoring and prediction system to provide a more comprehensive hazard alerting. Now let's go into more detail on how we generate the airspace safety margin forecast. Our current version forecasts 6 risk factors: ceiling and visibility at the airport, convective weather, arrival and departure traffic density, runway closures, and ILS outages. For each risk factor, we define thresholds for when its observation is classified as green, yellow, or orange. These individual risk factor categories are then aggregated into an overall airspace classification, once again using green, yellow, or orange. Now that's the abstract concept. The technical challenge is to find data sources for each of these risk factors, define appropriate thresholds for each risk factor observation, and develop a method for aggregating the set of observations into an overall airspace risk score. This graphic summarizes the data sources and how they combine with the analytics to generate the airspace safety margin forecast. The data come from diverse sources or asynchronous, and there's a lot of it. From SWIM, we process the TFMS and SFDPS, which come in a continuous fire hose. NOTAM's notifications come randomly when something is worth reporting. The weather reports arrive roughly hourly, but can be more frequent when the airport weather is dynamic, and the forecast can also vary. Convective weather forecasts are pretty much updated hourly. We also receive arrival traffic demand forecasts from the FAA's Command Center website, and we calculate departure demand using TFMS flight plan data. The primary output of this process is a 4-hour prediction of airspace safety margins in 15-minute periods, or epochs as we like to call them. Let me briefly mention that we have the ability to monitor the potential for pilot fatigue if connected to an airline crew assignment system. We could also add other information, such as whether crew were returning to duty after a long furlough. There have been recent reports of increases in mid-air collision alerts and rusty pilots forgetting to go through their full checklist. That information could be added to help monitor issues related to the recovery from the pandemic. I now want to show you some displays from the application we built to implement the airspace and flight safety margin forecast system. The current tool operates for 27 airports, and here's what we call our NAS-wide dashboard. It shows in one display the 4-hour forecast for all airports and allows the user to see right away where and when there might be a problem. Now suppose that I am in the Airline Ops Center. I see those red forecasts for Dallas-Fort Worth, and I want to know what is driving the prediction. I can get more detail by clicking on the DFW button, and it brings up this airport primary map. The left panel shows a vertical timeline of the 15-minute safety margin forecast. The map shows the geographic area with several options to display information on the screen. There is also a drop-down menu to show special use airspace, weather radar, wildfires, and other information. If I click on one of the epochs on the vertical timeline, it shows the status for the risk factor forecast that determined the overall safety margin score, such as ceiling and visibility, traffic density predictions, and convective weather. Individual flight risk forecasts are shown by selecting the flight list on the left panel. As we are not connected to an airline, these status indicators currently are just mock data. Now, if we were meeting in person, by now someone would have asked me, how do you determine when the airspace status is green, yellow, or orange? So let's dive into the details on that question. Our objective is to develop and apply an objective measure of safety margin and correlate it with the risk factors. We use buffer encroachments as our measure of safety margin. Think of the buffer encroachment as a deviation from the vertical and horizontal separation minimums. So this is where I have to make a strong qualifying statement that we are not detecting official loss of separation events. We interpolate between aircraft track messages and calculate what could have happened if aircraft continued on their current course and speed. If the aircraft does precisely what it is supposed to do, there will not be a problem. But if it is slow to follow the procedure or the controller commands, then the situation may become unsafe. So that is the sense in which we are measuring the airspace safety margin, or buffers. The FAA publishes a separation index and uses it to define separation conformance deviations, as shown in this graphic. Now you might say, but what about visual flight operations? Aircraft come much closer than these IFR standards, and the operation is considered safe. So we account for visual flight rules by allowing reduced separations under visual meteorological conditions. Using findings from a NASA research project, we identify a buffer encroachment under VMC when the separation index is less than 0.75 and under marginal VMC when the index is less than 0.9. Now let's take a look at some of the data. What we wanted to know is whether encroachments vary over time and across airports, and we wanted to see if there were impacts from the pandemic. These plots show mean encroachment durations per 15-minute epoch, calculated from April 2019 through July 2020. When we first calculated these data almost 2 years ago, we went, whoa! First, the data within airport varies considerably over the time period. The lines are jagged because encroachments are highly correlated with traffic counts. Secondly, there are some long cycles. Look at that Denver graph on the upper right side. Third, there is variation in the baseline level across airports, with Denver a conspicuous outlier on the high end. I should mention that Denver is also an outlier on other risk metrics that we track, and the Denver airport was mentioned a couple of weeks ago by the FAA as experiencing an increase in the number of mid-air collision alerts. The impact of the pandemic is obvious right away in the charts, as encroachment durations plummeted along with the number of flights in April and early May of 2020. But then look at Charlotte and Dallas-Fort Worth as traffic started to recover. Encroachment durations increased in the summer of 2020 above the previous levels, even though traffic was still at least 1/3 lower than pre-pandemic. Here are two more airports. Chicago O'Hare shows up as one of the lowest airports in terms of the encroachment durations, and Memphis is an outlier on the high end. So buffer encroachment durations are our primary safety margin metric. Let's see how it is correlated with the risk factors. This is where it gets pretty interesting. The pandemic completely messed up the validity of runway outages, and we're still analyzing the impact of convective weather. So that leaves most of the action to come from meteorological conditions, traffic density, and their impacts are substantial, as shown in this bar chart. We normalize traffic density across the 27 airports by using the traffic density percentile for each airport. That way we can compare Baltimore and Reagan National with Atlanta and Dallas-Fort Worth. As you can see, encroachment durations increase monotonically as traffic increases, and the durations increase a lot. And within each traffic density percentile, encroachment durations decrease as weather conditions improve. Put simply, if ceiling and visibility are poor and the airport is going into an arrival push, encroachment counts and durations will increase. These tables show the estimated exposure, and in the bottom table, the relative exposure difference. The exposure can be 50 to 60 times greater for the highest duration combination of conditions versus the lowest. With the limited time available, I cannot go into our current research that aims to add hazard exposure of individual flights to the prediction tool, but if you're interested and want to learn more, please contact me. I want to spend a few minutes describing our efforts to implement continuous real-time measurement of hazards and safety-related events in the terminal airspace. We started this effort after observing the buffer encroachment data I showed you a few minutes ago thinking that it would have been very useful back around May 30th of 2020 to detect those increasing encroachment durations at DFW and Charlotte and even some other airports. So the objective of this research is to detect trends and generate alerts when the frequency of hazard exposure and risk events increases enough to degrade safety margins. We wanted to build a system that operates continuously so you can see what happened 15 minutes ago or over the past 2 hours or the previous 2 months. Once again, we start with the NASA list of terminal airspace hazards and their classification into airspace, environment, and human workload. We have built a proof of concept using hazards from each of the 3 categories and adding in buffer encroachments as a cross-cutting metric. So here's the primary airport display. The graphs on the left show, going from top to bottom, late flight plan changes as a proxy for workload, turbulence reports within 50 miles of the airport, buffer encroachment durations, and deviation from runway centerline on final approach. The map on the right shows the airspace and locations of reported turbulence. Each of the hazards and risk metrics has a detailed set of graphs. Here is one for looking at encroachments and centerline deviations. There are a whole new set of graphical tools that are available for us to use in our web application, and they allow us to select a short time slice from one of the plots and zoom in to look at that period more closely. Let me wrap up. Say we've spent the past several years developing our vision for an aviation safety monitoring and prediction system. I'm very pleased to say that it is maturing very nicely. We have some predictive tools in place today, supported by a large, robust data processing and analysis infrastructure that allows us to add more hazards and risk metrics. It is all accessible through a standard web browser. We continue to work with NASA to develop and deploy new capabilities and welcome feedback from airlines on how we can make our tools more valuable and usable. We have a few videos to watch that are posted up on YouTube and our website. Please contact me if you want to learn more. Thank you very much for listening today.